I'm just going to give a whirlwind overview of some of the land DA work we're performing here in the dark group at NSF-NCAR. It's just my name up here, but there's plenty of people to thank, including the dark group and university collaborators. So for those of you who aren't familiar with our system, just a quick illustration. So we confront our prior understanding of the land state. On the bottom, there's an ensemble of CLM forecasts against at the top of the screen, which are observations. And then we create our ensemble spread through our ensemble DA approach through the CAM reanalysis ensemble as a boundary forcing. We advance that forward in time. And so we get to an observation, we extract variables in order to calculate the forward operator and perform spatial interpolation to get the expected observation. And then we update it. We apply increments to our ensemble, making it closer to the observation. So that's kind of prescribed here on the x-axis. And then using the background error covariance generated from our ensemble, we regress those increments on the rest of the Dart state. And that was kind of explained really well by Chun Chun's talk earlier today. And then we rinse and repeat. We go on to the next forecast step after that. And so just some of the examples of applications that we've been using here. So what is typical is a carbon monitoring forest management type application. So this is over East Africa, led by Cornell collaborators. And so they're ingesting leaf area observations. It's kind of reconfiguring the distribution of the leaf area and the assimilation on the left. We also include soil moisture SMAP observations here. Without soil moisture observations, it's a much wetter representation of the soil moisture depth. With soil moisture observations, it's a much drier representation. And so what that does is it reconfigures the carbon flux, the carbon cycle. So this is an example of the NEE across the East Africa domain. It's much more of a carbon sink, negative values when we don't include soil moisture. But when we do include soil moisture, it's much more of a carbon source with a spatial pattern. And what's reassuring is this sort of it reconfirms our understanding from top-down or atmospheric inversion estimates across a wider domain. This isn't apples to apples comparison, but they're largely consistent in spatial pattern. And so what we've also been focusing on is snow DA, creating a snow repartitioning scheme. And so if we apply that to the Western United States, what we can see here is it's taking away snow from the lower elevations based upon the CLM free run and adding snow at the higher elevations. If you look at the entire Western domain, CLM gives a premature melt off of snow here. This is the free run in kind of the yellow color. If we add those observations, we're increasing the snow cover into the spring snow melt periods. That fundamentally changes the carbon cycle in some areas. So just looking at the subsection of high elevation Colorado, we can see here the yellow is just LAI DA and the blue is added snow or SWE DA. We're increasing the snow across the entire year. This has downstream effects of increasing the soil moisture through the root zone. This relieves water availability according to CLM during much of the spring and the summer, and so it boosts the GPP. This isn't the same everywhere in the Pacific Northwest. It's not really changing the carbon cycle all that much, but it is having impacts on the surface energy balance. So again, we add snow through the DA to the system. This actually buries more of the leafed area, so the exposed leaf area decreases in much of the year, especially spring. This changes or increases the land albedo and changes the surface energy balance, so it decreases the sensible heat, so it has implications for land atmosphere coupling. We've also taken on looking at the impact that SIF, solar-induced fluorescence, can have on our carbon cycle. And so instead of parameter estimation, we're updating leaf nitrogen state content here. So here we have solar-induced fluorescence. We're confronting that with the harmonized SIF product, the dashed line. The red line, we're getting closer to that SIF product. It decreases the leaf nitrogen almost in half, rather dramatically. And because of the carbon nitrogen coupling in CLM, it actually is increasing like the leaf area, which is closer to observations here and bringing the GPP more consistent with the FluxCom. This is one of the better examples. This is just a C3 grass example. It's rather complicated because if you look at leaf nitrogen against other leaf nitrogen observations for C3 grass, it's not necessarily coming into better consensus. So Shuli Hugh is giving a talk on this later today or tomorrow as well. So shifting gears a little bit, we're focusing at NCAR at kind of the SPAD or system prediction timescale, so the sub-seasonal prediction timescale. There was a recent paper that came out in the AGU publication, the EOS, kind of focusing on this kind of forecasting desert, kind of the 2 week to 2 month time period in between numeric weather prediction and climate forecasts. We can apply DA, especially land DA, to have impacts on the atmospheric prediction for all these applications down here. I'm just going to show a few examples for subseasonal to seasonal atmospheric prediction. And so here we have an example of CESM2, and here we're looking at the anomaly correlation coefficient of the 2 meter temperature here as well. So the redder colors means there's better skill according to the ERA 5. And so what we're doing here is we just have two initialization approaches, one with the NSEP initialization, both for the atmosphere and the land. And here we're using our DART DA. So an atmospheric reanalysis and also using that as a boundary condition for the land. And the differences here, the red colors are the improved ACC skill when we're using the DART initialization. And so the direction we're going is to use direct land observations as well to improve this further. This is similar. This is work led at Auburn by Sanjeev Kumar and his group, but looking at kind of a similar thing and different initialization techniques across the continental United States, both with NSEP again and also with the DART CAM6. This is ACC in terms of forecast lead time and the soil moisture. So you can see if we're initializing with the DART CAM, this is atmospheric reanalysis, the soil moisture across the root zone is actually improving. And so why do we care about that in the subseasonal timescale? Because that helps, we think, improve precipitation forecasts, so water management type and drought forecasts. And so here are examples of high correlation where the soil moisture is strongly correlated with the precipitation forecast 3 to 4 weeks out. And so again, the goal is to move away from just atmospheric reanalysis, but also directly assimilate soil moisture in these areas as well. Beyond just CLM or CESM, we're applying this to E3SM. So this is an example of a subseasonal forecast led by the University of Utah, Jajapu's group. And this is specifically looking at forecast skill for extreme hydrology and tropical events when initializing with SMAP soil moisture data. So still on the kind of the initial phases of this project, this is just an example of a synthetic model data experiment applying this, and these are just the increments at random locations across the globe. We have advanced further. We have performed a synthetic data experiment based on a SMAP observation network as well. So kind of pushing forward with that. And then also we want to go into some parameter estimation work, which we haven't done traditionally, but is becoming super popular now. So just a thanks out to Natasha and those who put these kind of MIP intercomparisons together. We have an established technique for the ensemble DA, an augmented joint parameter state approach. And then we also have in-house collaborators with expertise like Daniel and Linnea and Katie with that have developed a CLM parameter sensitivity tool. So this is just an example of some of the looking at different sensitive parameters that we can select for our site level parameter estimation. We can drill down to different locations. What we still need to sort out is how to generate the ensemble spread. Will it be our traditional met forcing approach or perturb the parameters directly? We need to kind of adjust our code for multi-site optimization and also variable localization. Because it's an ensemble DA with sampling error, how do we limit the observational information to just the physically related parameters? So some things still to work out. And just a final slide here. I just wanted to give some notice to our most recent publication that was accepted in BAMS, and this is just describing the different progress we've made with our DART Ensemble DA tool. So a combination on the left of just the diagnostic teaching packages to go through the concepts of Ensemble DA, but also some of the advances in terms of new ensemble filters. This is a case of a neat application of streamflow led by Moha Gramsi, looking at different watersheds, different variable localization, and also different ensemble filters shown here. If you have any questions, just reach out to me. Thank you.